but I would like to thank the fields and especially the other organizers. I know I'm one of the organizers, but Mira really, and also Marcia, especially Mira and Marcia did a lot of the work for this. And so I'd like to thank them, and also the Fields Committee for helping so much with this. So this is the last day of the workshop, and it's my pleasure to introduce Antonios. I'm afraid to say your last name, Barbitsiotis, but I bet you, yeah, okay, I bet you can't say my name.
Yeah, it's no surprises. Yeah, Barbitsiotis.
Yeah, but I bet you I'm doing better than you pronouncing my name. So it's, yes, my pleasure to introduce Antonios. Antonios received his PhD at working with Monique in Amsterdam. And I actually looked at his thesis yesterday, and it was a very interesting thesis on looking at combinatorial conditions for low-rank solutions in semi-definite programming. And currently, Antonios is in Singapore at the University of Technology and Design. So he's an assistant professor there. And he works in multiple areas, in the convex optimization, obviously, and semi-definite programming, but also in combinatorial optimization, foundations of quantum mechanics, and machine learning. So I guess I'd like to just let you go ahead, and everybody can see the title of your talk. So I'm looking forward to your talk. Please go ahead, Antonios.
Yeah, thank you. Thank you so much. Okay, again, I hope slides are okay. I hope everyone can hear me. So let me start again by thanking you all for accommodating this talk, even because again, Singapore, there's 12 hours time difference. And I do apologize for not really being able to attend the talks, but I mean, somehow, the conference starts 9 p.m. Singapore time. So it's very difficult. Okay, so in any case, today I'm talking about kind of some new things we are working on together with Yong Sheng from the National University of Singapore. So it's going to be about a non-commutative kind of extension of Lee-Song's algorithms for NMF, but we're kind of tailoring it now for the positive semi-definite matrix factorization problem. Okay, so so this talk is going to be about an algorithm for PSD factorization. So let's kind of first start by defining what this problem is. So so in this setting, right? So we are giving as input, like a matrix X. It's a rectangular matrix M times N. And its entry-wise non-negative. So the entries of X are non-negative. Okay, so that's our input. And we are also given as input some kind of user-specified parameter R. Okay, so this R is some natural number, 2, 3, 4, 5, or your favorite natural number. So these are the two things we have. And what we're kind of asked to find is two families of PSD matrices. So we have the A's and the B's. And we have, notice we have one of the A's for each of the rows of X, and we have one of the B's for each of the columns of N. For each of the columns of X, okay, and these guys, they need to be positive semi-definite, and their size needs to be R times R, okay, the user-specified parameter. Okay, and the main thing that we're asking from these two families of matrices is that for the ij entry of matrix X, I want that to be equal to the trace net product between AI and Bj. Okay, so that's the goal here. Okay, we're trying to find these two families of PSD matrices that somehow recover the entries of the matrix X. Okay, and again, R is fixed. Okay, it's some kind of someone has told me find a 5-dimensional PSD factorization. So that's what we're looking for, and now it's kind of easy to see that you can always if your R is like less than minimum number of rows and number of columns, you can always find the PSD factorization. That's not that difficult. Okay, but what is more difficult is to find the smallest R for which your matrix actually admits an R-dimensional PSD factorization, and that is known the PSD rank of X. Okay, it's a very, very nice, very cool quantity. And because it's kind of related to all kinds of stuff, and but my two kind of favorite applications. So the first one is that PSD factorizations in general, so they kind of capture the expressive power of semi-definite programs. Again, semi-definite programs, it's just linear optimization over the cone of PSD matrices. Okay. And what I mean by that, there's some kind of this canonical correspondence that, if you have some polytope, you kind of associate a matrix to it, the so-called slack matrix. And then, PSD factorizations of the slack matrix, they give you a way to express your polytope as a projection of an affine slice of like a PSD cone, of the size of the PSD factorization. Okay, but somehow also there's some kind of very cool applications, also somehow very close, very interesting connections between PSD factorizations and somehow quantum information theory. Okay, so somehow again, if you have like some kind of matrix corresponding to a probability distribution, a PSD factorization, kind of gives you a way to realize this thing as some kind of quantum protocol. Okay, but again, I don't really have time to go into the details. But somehow, okay, this kind of PSD factorization is kind of relevant for kind of many areas. So both optimization and information theory. And perhaps, the more geeky mathematical reason is that somehow PSD factorizations are like a non-commutative analog of non-negative matrix factorizations. And what are these? So what is a non-negative matrix factorization? So it's basically the same thing. It's kind of the same thing as we had before. We have like a matrix X, which is entwise non-negative, and some user specified parameter R. But before we were trying to find PSD matrices that somehow were kind of realizing the X. In the context of NMF, we are trying to find non-negative vectors, R-dimensional entry-wise non-negative vectors. And we have the A's and the B's. The A's kind of label the rows of X, the B's label the columns of X. And what we're asking from these vectors is that the AJ entry of X is given by the inner product between AI and BJ. Okay, so this is like the NMF problem. And if you just think about it for a second, you kind of see that NMFs, they're basically very, very, very special PSD factorizations. And it's exactly the case when you kind of restrict the PSD factors, the AIs and the BJs, to be diagonal PSD matrices. Okay, because diagonal PSD matrices, they're nothing but non-negative vectors. So NMF is basically it's like a special case of PSD factorizations. Okay, but NMFs are somehow like very, very popular. I would say much more popular compared to PSD factorizations. Okay, and they're basically, and the popularity is mostly because somehow you can kind of use them as a dimensionality reduction tool. Okay, and that kind of brings about many cool applications in areas like document clustering, musical analysis, and many others. And the reason somehow why NMFs somehow come into play is somehow because they give this kind of very beautiful parts-based representations of your input data. Okay, so meaning that kind of you kind of explain your data by kind of adding, by kind of aggregating some like a finite number of atoms. Okay. Now, again, this is kind of vague, and if time allows, I will kind of meditate a bit more on this. I will explain kind of more precisely what this means. But somehow, again, like NMF is like a very important problem, like beyond optimization, right? So it's very important in engineering, and it has many applications. So okay, so somehow, okay, so we introduced the PSD factorization problem. So and somehow we kind of also introduced NMF and kind of realized that there's a special case of the PSD factorization problem. So now let's kind of slowly work towards kind of coming up with an algorithm for finding PSD factorizations. Okay, and so again, in this context, again, always remember that R, so the size of the PSD matrices, so that is fixed. Okay, so we have kind of made a choice. R is like 5 or 7 or 2 or whatever. Okay, so we have made a choice, and now we are trying to find an R-dimensional PSD factorization. So now, okay, so obviously, like the canonical starting point would just be to set up some kind of non-convex problem where you kind of minimize the the square loss over all the entries of your matrix. Okay, but of course, there's so much you can do with this, right? So, but again, like the standard thing you might do is you're going to try some kind of coordinate descent approach to solve this problem. And probably the first thing you would try, if one showed you this, it would kind of do some kind of alternate optimization between the A's and the B's. Okay, so you kind of alternate between minimizing with respect to the A's. Okay, it's this n PSD matrices, A1 up to AN. Okay, so in this context, like in the first program here, the B's are fixed, and I'm just minimizing over the A's. And after I update my A's, I kind of minimize again over the B's. Okay, so just do kind of coordinate descent where I kind of have two blocks, the A's and the B's. So that would be kind of a natural thing to do, right? So Okay, and again, like I don't want to be talking about both of these things, so let's just, we're just going to focus on one of them because everything is entirely symmetric. Okay, so for concreteness, let's just say, we have updated the AIs, so the AIs are like fine, and now we kind of need to worry about the BIs, the BJs. Okay, so I kind of need to solve this problem. Okay, and then you kind of stare at this for a second, and you basically realize that this guy is separable with respect to the BJs. Okay, so so in the end of the day, you basically just need to solve this for every for each, and here you only have one matrix variable. You have the BJs. Okay, and just to kind of to simplify notation, let's just omit the dependency on J, and I can just rewrite this as minimum x minus AB Euclidean norm squared. Okay, where here this is just simplifying notation, where this small x here is just the jth column of the matrix X. Okay, these are exactly all the entries that appear here, and script A is this linear mapping that you feed it a symmetric matrix of size R, and it spits out the inner products of your matrix B with A1, A2, and AN. Okay, with these fixed PSD matrices that we have kind of updated already in the previous step. Okay, and this norm is just the usual Euclidean norm. Okay, and okay, and again, hopefully you see that this is just notation. Okay, so this is just exactly the same as this program. Okay, so long story short, right? So doing this kind of coordinate descent approach, right? So this is the type of thing we need to solve. Okay, we need to solve this. I mean, at each iteration, we will need to solve an optimization problem of this form. Okay, so again, any questions, comments, please just interrupt. Okay, feel free to interrupt. I'm not really keeping track of any of the chat. So okay, so now these like sub problems we encounter, they are convex. Okay, and in fact, this is what we would call like a convex quadratic SDP. Okay, but okay, I mean they are convex, but we don't really have a closed form solution for these guys, right? So at the end of the day, if this was your subroutine and your coordinate descent, you would need to be using some kind of numerical optimization to solve this. Okay, right, so and somehow, there is some work out there, like dealing with, how to find PSD factorizations, and all of them, at least to the extent that I'm aware of, right? So, this is basically the starting point, okay, doing like, coordinate descent. So, and ending up with a problem that looks like this. And, in one case, like let's say in this paper by Vandele, Gillis and Gliner, they give two algorithms for this problem. So this was the first paper, right? So somehow the algorithms they give, they're kind of simple, right? So they give the first one is like a projected gradient method, where you take a gradient step and then you project back into the PSD cone. The second method is like a method that kind of also allows you to keep track of the rank of the PSD factors, okay, which is something I haven't really talked about, because okay, the idea here is that in the PSD factorization, so for the way I introduced the problem, I only fixed the size of the matrix. Okay, so the size is R, and that's fixed. It's like 5. But perhaps, and depending on the application you are looking at, you might also want to talk about the rank of the PSD factors. Okay, so they're like.
Can I ask you a question?
Yeah, go ahead. Yeah.
So you're saying this is a convex problem, but you're restricting the rank to be R, and it's still convex?
No, I haven't restricted the R. Right? I haven't restricted anything. Yeah. So when I say convexity, I'm talking about this problem here.
Oh, okay. Right? Sorry.
Yeah. So I'm just saying here. I'm just talking about the second algorithm here. Okay. I'm just saying. Okay. First of all, I'm saying that there are certain applications where besides. Okay, so you want to talk about you want to find the PSD factorization of size R, but you also want to say something about the rank of the PSD factors. Okay, so somehow low rank, and in this context, so basically you would go here and you would do like like the typical let's say Burel-Monteiro change of variables. So you replace B with like a UU transpose, where the intermediate dimension is the rank you care about. And this is exactly what they do here, okay? And then they basically solve that using coordinate descent with respect to all of these new variables that you introduce, okay? So that's what's happening here. And in like some kind of later papers by Fevot, which works a lot on music applications in musical analysis, together with Vincent Tan and some other collaborators. They give some other algorithms for solving, like this guy here. And these algorithms basically, they kind of just come from the fact that, somehow they kind of realize that, this is the type of thing that you get, working in signal processing when you work with problems like affine rank minimization, phase retrieval, and stuff like that. Problems of this kind of type. These are the type of relaxation that you kind of end up with. Okay, so basically, they kind of look into the signal processing literature and they kind of dig out algorithms, for affine rank minimization and phase retrieval, and they kind of apply it to this problem. So these are like the kind of the existing things that are out there. So okay, so but now what we're going to do is going to be kind of different. Okay, so we're going to be using we're going to try to solve this problem, but using the majorization minimization approach, which I'm guessing some of you might have heard, maybe in the context of Gaussian mixtures. Probably that's a type of thing many people have probably seen. Okay, but in any case, like in one slide and without any pictures. So the MM approach, kind of on a very high level, okay, it's kind of a very generic method for kind of solving an optimization problem. So let's say you want to minimize f over some set script x. Okay, and if you want to apply the MM approach, what you need to find is you need to find the so-called auxiliary functions. So you need to find a family of auxiliary functions. So let's say one for every x in your domain. Okay, and the auxiliary functions, they need to satisfy the following two things. Okay, so the first one is what we call the domination property. So the auxiliary function just needs to lie entirely above your function f. Okay, so f of y is upper bounded by ux of y for every y. And the second thing is that at the specific point x, when you evaluate the auxiliary function at x, it needs to touch your function. Okay, so these are like the two things. Okay, that you need. And as long as you have these two properties, then I mean essentially you kind of have an algorithm. But again, this is all like high level, right? So and the algorithm is the following: it's like you have your kth iterate, which is xk, and then what you do is like you kind of set up the auxiliary function corresponding to xk. You minimize that, and that is the xk plus 1. Okay, so that is your new iterate. And I mean, and it's like it's kind of trivial to see that like if you do that, this kind of update rule, somehow along the trajectories of this update rule, if you will. So the function f is non-increasing. Okay, so f of xk plus 1 is upper bounded by f of xk. Okay. So okay, but again, like now, of course, now to make this work, there's a lot of things here. Obviously, here, somehow the auxiliary functions need to be tractable in some way to be able to even kind of calculate, this, xk plus 1. Then there's also all kinds of convergence issues because okay, so here we kind of see that f is non-increasing in value, but there's issues of whether x is actually converging to a minimizer and stuff like that. But okay, but that's basically all I'm going to need from MM at the moment. Okay, so this is basically the definition. This is like the MM framework. Okay, it's just a generic framework. Okay, but now I'm just going to show you how we can actually apply the MM approach to solve this kind of sub-problem of interest that we encounter when we try to do PSD factorizations. Okay, so again, the first thing we need to do is we need to find an appropriate family of auxiliary functions, right? So that's the first thing we need to do, right, okay. So now like the kind of the baby lemma, which is kind of motivate somehow the correct. I guess this is like step number 0, okay, which is going to lead us to the algorithm. Is that if you could find like a linear mapping, which is invertible. So that t is upper, t minus a transpose a is positive. So in other words, t is at least a transpose a in the PSD order. Okay, so then the function of interest is non-increasing with respect to this update rule. Okay, so and this is just very easy, and this just follows straight from the definition of the MM framework, because, right, so, this is our objective function, okay? So, and again, notice that I'm not worrying about PSD-ness at this stage. It's like I completely forgot about the PSD-ness, and I'm only like minimizing over symmetric matrices. So this is like unconstrained. So this is my objective function, and I'm just gonna do a Taylor expansion at B old, okay? So, and I'm just gonna get this identity because my function is a quadratic. And then, right, so, but then I am assuming that T is larger compared to A transpose A, and that's going to give me basically this inequality, okay? Okay, so essentially I just replace A transpose A with T here, which is fine because T is larger compared to A transpose A. And obviously, if you plug in B old for B, we have equality, okay? So these guys here, so this is really a valid family of auxiliary functions, okay? And again, if I just follow the recipe of the the MM approach, right? So the MM approach tells me that your new iterate is the minimizer of the auxiliary function at the old iterate. Okay, and of course that's something you can calculate, and this is what you're going to get. Okay, so again, if you had this T larger compared to A transpose A, so then again you can kind of bound the Taylor expansion, and you just minimize that, and this is the type of thing you get. Okay, hopefully this makes sense. Again, any questions, feel free to ask. But like, okay, but fine, that's like okay, but that's definitely not really what we want, because of course we are going for PSD-ness, right? I'm trying to find a PSD factorization of my matrix, and this type of update definitely is not going to guarantee any type of PSD-ness, right? So even if the old iterate B old was PSD, I mean, there's just no way that B new is going to be PSD. Okay, so then the way we're going to try to enforce PSD-ness is by basically enforcing additional structure. So we're going to ask more things on the linear map T. Okay, so for now we only ask that T is larger compared to A transpose A in the lower order, but now we're going to ask two more things. And I mean, somehow kind of no surprise, we're going to basically ask that T kind of acts as like congruence with a positive definite matrix Q. So that's the first thing. That's the first additional kind of requirement. And the second requirement is that when I hit A transpose A B old with T inverse, I want to get exactly B old. Okay, so okay, so these are the two things. And they look technical, but I mean somehow let's see where these things come from. So somehow they don't come from nowhere. They basically come from this update rule, which we had. Now again, remember T was linear, so I can kind of distribute T. And now you see that condition 3 basically says essentially that the first two terms here, they're going to cancel, they're equal to 0. And then so the only thing that remains is that B new is equal to T inverse acting on A transpose X. So this is what remains just by using 3. Okay, so if T satisfies 3, so then this is my updates. Okay, and now the last thing here to notice is that if you kind of work out what A transpose X is, well, A transpose X just basically forms this conic combination of the AIs. Okay, and remember the AIs, they have been updated in the previous step, and they are PSD. So vector X is supposed to be the jth column of the input matrix, which is non-negative. So this is a conic combination of positive semidefinite matrices. So it's itself, this is a PSD matrix. Okay, and then basically I have a PSD matrix and I hit it with T inverse, but I have assumed that T inverse kind of acts as congruence with a PD matrix, so PSD-ness is preserved, right? So somehow we are in good shape. If T satisfies these two additional properties, so then this is the update, and this update is PSD. Okay, so I hope that makes sense. Okay, so okay, and then basically the last thing is that, right, so again, kind of summarizing, right, so if we have a T that satisfies basically these three things, so then somehow we are in good shape, right? So essentially we have an MM algorithm. Okay, but then of course you might wonder, can you actually find a T that kind of satisfies all of these things? And as it turns out, not only you can, but it's also uniquely specified. Okay, and in the sense that so this Q here is going to be uniquely specified. Okay, so the Q matrix, and that's going to follow by essentially by the definition of the matrix geometric mean. Okay, which is algebraically this is the following, right? So if you have two positive definite matrices, so this is the matrix geometric mean, okay, kind of algebraically, but I guess more relevant for us is the following definition, that if you kind of set up this kind of Riccati equation in the matrix variable X, again, C and D are positive definite, then you know this beast here, the geometric mean, is the unique positive solution of this matrix equation. Okay. Right, so and then if you kind of, if I just go back one slide, right, so if you basically kind of combine these two things, right, so you'll see that you know, if you substitute T inverse with as congruence with Q inverse, and then you use equation 3, you'll basically get that Q actually satisfies this equation here. Okay, or in other words, exactly by the unicity property of the geometric mean, you basically see that Q is nothing but B odd inverse geometric mean A transpose A B odd. Okay, so Q is the matrix geometric mean of these two guys here. Okay, so okay, so that's yeah. Okay, yeah.
So you got a, I guess, yeah,
sorry.
Time is going.
Okay, okay, sorry, my phone.
Take another 2-3 minutes, and maybe we'll.
Yeah, it's no worries. Yeah. So thanks. Okay, so Q is uniquely specified, and again, it's given by the mean between B odd and A transpose A B odd. Okay, and basically that's basically essentially we have the algorithm, right? So and again, I mean, it's a bit of a mouthful, but all of this is saying this is just the formula, right? So it's just T inverse acting on A transpose X. If you remember that X is the jth column of your input matrix, and then if you also remember that we asked for T inverse to be of the form so this is going to be Q inverse acting on A transpose Y. Q inverse, and Q we kind of agree that is given by this geometric mean. So this is basically the algorithm. Okay, so this is the algorithm you get for updating your PSD matrices. Okay, and of course there is okay, so I don't really have time to go through the details, but of course there is something remaining to show, which is somehow the non-trivial part of I guess the technical part of the paper, is that you still need to show the domination property for this specific choice of Q. You get this mapping, okay, and you do need to satisfy, again, A is fixed, and you do need to satisfy that the domination property, meaning that T is larger compared to A transpose A in the PSD order, okay. And I mean, that takes some work. But somehow, you're gonna need to invoke like Lieb's concavity theorem and, von Neumann stress inequality, and, patch things together in a nice way. And it kind of works out beautifully. Okay. Okay, and maybe some comments about this algorithm. Okay, it's like kind of simple and easy to implement, right? So this algorithm is really simple, right? Because I mean, it's basically, it's just this formula, and it's just a matter of having a subroutine for calculating geometric means. So there's no projection on the PSD cone or anything like that, at least not explicitly. Okay, the PSD-ness of the iterate is automatic. Okay, another cool thing is that if you actually look at fixed points of the update rule, they are basically points that satisfy the KKT conditions of the optimization problem we are trying to solve. And another very cool thing, which kind of we like a lot and we are trying to explore in applications, is that this algorithm actually also respects block diagonal PSD factorizations. So if you need, meaning that if you initialize with a certain, because you do need to initialize, and if you initialize with a certain block diagonal pattern, so this pattern is gonna kind of it's gonna remain as an invariant throughout the execution of this algorithm. Okay, so this is gonna kind of allow you to calculate block diagonal PSD factorizations, which are relevant also in quantum and for various reasons. Okay, and I don't know, and if I have like for my last slide, I guess, because I'm out of time, I'm not going to do Lee Song any justice. Lee Song's algorithm is somehow, it's like super useful and super widely used algorithm for calculating non-negative matrix factorizations. Okay, and this is like this is how it looks like. And again, it's kind of an MM algorithm, so it has like all the properties you're going to expect an MM algorithm to enjoy. Okay, but the cool thing is that if you basically just take our algorithm and you just specialize to diagonal PSD matrices. Okay, so you just recover you recover Lee Song's algorithm. And again, I'm not doing Lee Song any justice here. I mean, this paper is like super important. It's like more than 10,000 citations. Okay, but again, special case of our algorithm, when you plug in diagonal PSD matrices, you do recover Lee Song. Okay. Okay, and we have some numerics. Somehow things are nice, but we're still kind of trying to apply this for more like more and more examples. And two things we are working on, and I mean, I guess maybe I focus on the second one, is that we have been able to kind of to extend this also for arbitrary symmetric cones. Okay, so if you were trying to find PSD factorization, I mean conic factorizations for symmetric cones, so then somehow things kind of work out. Although now you have to go through all the kind of Jordan algebra language. Okay, so that's all. I'm probably 1 or 2 minutes late, so I apologize for that. But thanks a lot, and please, if you have any questions, please go ahead.
Thank you very much.
Yeah.
For a very interesting talk. And I guess we have time for one quick question. We also will have time for questions after Anthony's talk. So hopefully you can stay around.
Yeah, no problem.
Yeah. Anybody have a quick question?
How would this compare to just off-the-shelf convex optimization?
I mean, I don't know. That's probably hard to say. I mean, you're probably gonna do You're gonna see extensive experiments when the abstract when the paper comes out. I mean, I guess the main difference I would say, because again, even you can ask the same question for NMF, right? So you could still be doing NMF by solving essentially non-negatively squares. Okay, but that's kind of a completely different beast, right? So it's going to be about interior point algorithms or whatever numerical subroutine you are using. I guess this has the advantage that it's just easy to implement. Even Lisong, you just look at this, whatever, you just implement this. It's just, it's like 5 lines of code, and kind of runs well. Of course, you don't have very good theoretical guarantees. You only have the guarantees, whatever they are. Yeah, but I mean, I think this, I mean, the advantage here is simplicity. Okay.
Thank you again.
Yeah.
So hopefully we can ask some more questions.
Yeah, absolutely. I'll be around.
Yeah, during the break.
Yeah.
Okay, so Anthony, do you want to try?
Yes.
Sharing your screen? Yes, it looks
see?
good. And the slides move? Yeah.
Yep.
Yes, all right. Okay, so yeah, it's my pleasure to introduce the next speaker as well. So this is Anthony Man-Cho So, and he's at the Chinese University of Hong Kong. Anthony got his PhD in 2007 with Yin-Yu Yi at Stanford University. And I guess one of the things that sort of related to the previous talk, at least to the previous speaker's PhD thesis, is Anthony has a very interesting survey paper with Alex Lemon and Yin-Yu Yi on low-rank semi-definite programming. So this came out in the Foundations and Trends in 2016. And of course, he has many other contributions and over the many years. So Anthony, we're starting a little late, so it's 5 minutes after. So you have at least till after half hour. So please go ahead.
All right. Thank you, Henry. Can you all hear me? Is it all right?
Yes.
All right.
I can hear you. Yes.
Okay, great. Thank you. So thank you, Henry, for the introduction. And thank you for all the organizers for inviting me to give this talk. So this one will be more on the distance geometry side. We touch a little bit on semi-definite programming. And this is definitely a problem from application. So it is the source localization problem in signal processing. So this is a joint work with my PhD student, Mandy. So I believe she's also in the audience. So let me talk about the problem. So it is rather simple to describe. One is interested in localizing a signal emitting source using a number of sensors with a priori known locations. So here, I guess I would have a slightly different usage of the term sensors in terms of sensor network localization. So here, what I refer to as sensors is really what is referred to as anchors in the sensor network localization literature. So the sensors, the locations and the source is the thing that you want to find the location of. So this is a signal emitting source. This is known as the single source localization in signal processing. So a very simple problem. I'm not even talking about localizing multiple sources. I have only one thing to localize with a network of sensors. Now, of course, the problem here is the measurements are often noisy. Typically, if they are noiseless, of course, you know that with 3 sensors or 3 anchors, you will be able to localize the source. But here, the trick is that these measurements are noisy. And in a moment, I will talk about the measurement models. So in the signal processing literature, there are many different types of measurements. So here we are using the so-called time of arrival. It is the time taken for the signal to reach from the source to the sensor. And so multiplying by the signal propagation speed, you actually get the traditional range measurements. And I will explain this in a moment. But there are many different types of measurements in signal processing literature. Some of them depend on the angle of arrival and other more fancy measurement models. Here, we just focus on the most basic one. So this problem has a lot of different applications. You can also see some of the applications in these 2 survey papers on IEEE Signal Processing Magazine. So acoustics, emergency response, and also target tracking. Target tracking, of course, is a dynamic setting. And so I will talk about this in the second part of this talk as well, once we study a little bit more about the geometry of this time of arrival based source localization problem. Now, so here is the formal introduction of the measurement model. So this is the time of arrival measurement model. So here, X star is the source. So I will use star to represent the ground truth. So this is not known to you. This is the thing you want to estimate. You have a bunch of sensors whose locations are known. So they are denoted by AI. And so as you can see from this expression, you measure the distance and then divided by c, which is the signal propagation speed. You get a unit of time. And so that is the time of arrival. Now, of course, as with most measurements, they are corrupted by noise. So here you have a measurement noise that is denoted by eta I. Okay, so this is a measurement error. At this point, I do not assume anything about the measurement error yet. So in particular, I do not assume any statistical properties on it. So this is the basic model. Okay. And so here, of course, the application of interest mostly will lie in 2 dimensions. So n equals to 2 or 3. But here we just formulate it in a general dimension. So here n is the dimension of the ambient space. Okay. And so from this, it is easily seen. If I multiply both sides by c, then I basically get range measurements. And so this is the usual data we have for our sensor network localization problem. You have the true distance plus a noise that equals to your range measurement. Okay. Now, so with this, then it is rather simple. So one can formulate various objectives to try to estimate the ground truth X star. Here is a natural least squares formulation. So here, this is my loss function f. So I want to find x so that the difference between the measured, the obtained measurement and my measurement based on x is smallest. Okay, and so here I would denote the optimal solution to this problem as x hat. And so, of course, there could be multiple, but so I would just not assume any uniqueness at this point. So this is the least squares formulation. This is motivated also from the measurement models used in the signal processing literature. They will usually assume that the WIs are IID Gaussian random variables. And in that case, this is actually the maximum likelihood formulation. Then X hat will be a maximum likelihood estimator of X star. Here I assume that the noise are IID, but in case they are just independent but not identically distributed Gaussian, so then there will be a weight in front of each term. Here for simplicity, I just assume that they are IID. So this you can formulate it as this basically unweighted sum. So every term has a weight of 1 basically. Now, so this formulation, so it's motivated, of course, by this statistical consideration, but of course we can just study it as a least squares formulation. The thing to note here is that this is non-convex in general. That is not surprising. So most of these localization optimization formulations of localization problems are non-convex. But this is also non-smooth. So here this involves a 2 norm, but not its square. So this is also different from the difference of squares model, right? So in some of the sensor network localization literature, sometimes another loss function is used where you minimize the sum of the square of the squared differences. So here it would be x minus ai 2 norm square minus ri square, okay? So we are not considering that model. We are considering this least squares model. So this is also a non-smooth problem. Okay. In general, this is slightly challenging to solve. And in the early days, people basically tackle it using semi-definite relaxation. This workshop is about semi-definite programming. So I should at least put out a slide on semi-definite programming approach to this problem, although subsequently I will discuss some alternative approaches to solving this problem. So I think for the semi-definite relaxation, the tricks are by now rather standard. Of course, in the early days, people, when they first discovered this, this is more exciting. I guess by now it is kind of well-known techniques. So basically, how do you handle this non-square 2 norm term? Well, basically you introduce a new variable called yi. And so you want basically yi equals to x minus ai 2 norm. So here yi square equals to its square. And then basically you observe that the objective function becomes yi minus ri square. And so one can basically write it out like this. And so that is the equivalent formulation introducing an extra variable. And from this, it is really standard to just relax it into a semi-definite program. So this is one of the relaxations. Here, the black dot is just the trace in the product, just like what Antonius just talked about. And this is the semi-definite relaxation. Okay. Now, of course, one can be much more fancy than this. In the case of sensor network localization, where one has multiple anchors and multiple sources, one can still formulate something similar. So that is, and many of you in the audience have worked on this as well. That is very familiar to many of you. So the upshot of this, of course, at the beginning is that it is theoretically tractable, meaning you have a polynomial-sized SDP. So you can solve it up to any accuracy in polynomial time. But if you just plug in standard solvers, so from a practical perspective, it is not very scalable. Okay, so as your problem gets bigger, then the off-the-shelf solvers will get more will be a little bit more time consuming to tackle them. But I should also mention, of course, one can develop specialized solvers exploiting the structure of the semi-definite relaxation to get speed up or improve quality. And in particular, I think in the audience, Henry and Nathan Chrislock have worked on this, exploiting the different structure, incorporating the geometric information to help in the solution of the SDP. Okay, so those definitely could be more efficient than just plugging in a standard off-the-shelf solver. And interestingly, even for this very simple source localization model, so remember, I'm just trying to localize one point, right, one source. And so for this SDR, there is some nice theoretical properties established in this paper by Amir Beck and co-authors. And so in particular, they prove that if you solve this problem to optimum, then the optimal Y matrix will be rank 1. So this block, the capital Y, will essentially be equal to Y transpose. Okay, so that is some of the theoretical analysis that they did. Now, so moving onwards, what we are really interested in is whether we can. So the flavor is really similar to the previous talk of Antonio's. So whether we can find some lightweight and or first order methods, simple strategies to solve this problem. So for example, treating this as an unconstrained minimization problem, whether I can apply some simple methods, maybe gradient descent, first order methods to tackle it. So this has also been done in 2008 around. I guess this is one of the earlier works. I won't say this is the earliest work. This is again by Amir Beck and co-authors. They developed a fixed point or gradient descent scheme for solving this problem. So again, this is the objective function I want to minimize. Here there is a little annoying part, is that this part is non-smooth at the AIs, correct? So if X is one of the anchors positions, one of the AI, then the function is not smooth there, okay? So let us for simplicity, try to ignore that issue. Assume that you have an X bar that is a stationary point of F, and it does not coincide with any of the anchors position. Then you can just write down its first order optimality condition. So it will have to satisfy basically this relationship. So this is just by taking the gradient of this. So this is straightforward. And so you observe this kind of expression. And so from here, the paper observed that essentially this is a fixed point equation. So X bar equals to a function of X bar. And so this naturally motivates a fixed point scheme. So here I highlighted in blue where that is where you replace the variable, right? So a fixed point scheme is very simple. So at each iteration, you apply the mapping to it to get the new iterate, see if they are the same. If they are not, then repeat, right? So here xk is here, you apply the map to it and you get xk plus 1, okay? And then you repeat. And so interestingly, this fixed point scheme, again, shown in this paper, is equivalent to a gradient descent scheme. So basically, you can derive that this is just this gradient scheme with step size 1/2m. So I should mention m is the number of anchors. Okay, so number of the points whose positions are known. Okay, so this is the scheme. With the study of first order methods, one is interested then in convergence behavior. In general, convergence behavior, there are a couple questions that one can ask. First of all, whether it converges at all, right? If it converges, where does it converge to? And then if you can answer that, you can be even more ambitious and ask what is the rate, right? How fast does it converge? So for this particular scheme, in this particular paper, they only establish subsequential convergence. So basically, they show a result in the following flavor. So essentially, every limit point of this scheme will be a stationary point, okay? But they cannot say that the sequence xk itself converges to a stationary point. Okay, so there is this very little subtle difference. So again, what they prove is every limit point of this sequence is a stationary point, but they cannot guarantee that the whole sequence converges. Okay, now, but this of course is rather straightforward to compute. As you can see, you just add up a bunch of terms and then do the update. So this is rather tractable, and so it can solve rather large scale problems. So then, with these results in mind, our I guess research agenda would be: can we say more, right? So now, if you look at the localization problem, so if you look at just this objective function as it is, then of course in the worst case, it can be rather challenging, right? So it will be NP hard. And if all the data are given in a worst case sense, then of course, probably there aren't much you can say. But what we are motivated is from the signal processing literature. They have a very well-defined, well-accepted generative model of the source localization problem. Okay, so the RI is not arbitrary. The measurements, the distance measurements are not arbitrary, but it is the the real measurements plus a bit of a noise. So it is not arbitrary data. So there are a couple questions that we can immediately ask. So the first one is not so much related to, well, it's still related to this model, but probably not so much related to the algorithm, and that is the estimation performance. Okay, and so that is how far is x hat from x star. Now, so in case you are confused now, so let me remind you what x hat and x star are. Okay, x star is the ground truth, right? So that is the thing that you want to estimate. So how are we proposing to estimate it? We are proposing to estimate it by minimizing this loss function f, and x hat is an optimal solution to this loss function. Okay, now, so I'm not saying I can compute it efficiently or anything. I'm just asking this: if I can compute it, if I can compute x hat, how far would it be from x star? And so here is one thing to pay attention. First of all, they need not be the same, right? Because the ground truth could be very far from the optimal solution to the least squares estimator. They need not be the same, right? You can think about the situation where there is a huge noise Wi, which completely drowns out this part. And then there is no way you can know what x star would be. And so in that case, x hat will probably be very different from x star. Okay, so here this question would be in terms of estimation performance. Say if I make some assumptions on the Wi, perhaps they are not too big, whether I can bound how far x hat is from x star. Okay, so that is the question. So in what follows, I would call the x hat the least squares estimator. This is very natural because this is the optimal solution to the least squares problem. Okay, so the estimator need not be the same as the ground truth. Now, then we can focus more on the algorithmic issues. So if you are thinking about the gradient descent scheme that we just introduced, so then there are various questions you can ask, right? So for example, we are solving a non-convex problem, so initialization will probably matter. And so how should we initialize the GD scheme? Okay, so whether I can initialize it so that it can converge to some favorable points. And the next question then would be the convergence performance. So now I run this gradient descent. So I generate a sequence xk. So does it converge, right? So the previous result in a back and co-author's paper, it didn't say it would converge. It only say if every limit point will be stationary. So if we can show that this converge, then what point does it converge to? And as I just mentioned, we can be a little bit more ambitious and ask at what rate. Okay, and so these are the questions that drive our research, this piece of research. Now, so before we answer this question, let us see whether it is at all possible or whether there are interesting phenomena we can observe that give us hope that maybe something nice can be said about these things. So we did an experiment. So this is, of course, synthetic data. So very few sensors. So again, sensors are the things that position are known. So again, taking a random model. So I just randomly distribute on a circle. And then the source is generated within a square. And then the noise, I set it to be Gaussian with sort of a medium and towards the small size noise, and then I run for 1,000 times. And then this is what we observe. So this is the number of iterations on the x-axis. And on the y-axis, we are comparing on log scale the difference in the objective values. So f star is a kind of the lowest value we can find. So we pretend that that is the optimal value. And then as we do the iterations, we plot the progress of the algorithm. Okay. Now, so if you are familiar with this kind of diagrams for first order methods, so this look like more or less a straight line, right? So it suggests what is called a linear convergence of this algorithm. And so linear convergence in this setting, that probably suggests that there is some very nice geometry of the objective function. For example, it satisfies strong convexity, or perhaps if not strong convexity, it may satisfy some error-bound conditions, okay? And so that is how one would observe this kind of behavior. Otherwise, it would be more of like a sublinear behavior where the curve drops fast first and then flattens out as it goes on, okay? And if you were in Antonio's talk previously, I think some of the pictures he showed is exactly that type of behavior. So you drop fast first and then it flattens out. So that is more typical of a sublinear convergent algorithm. All right, so this is suggesting something, okay? And so the question then is whether we can dig it out and characterize it, formalize it, and find a theorem about it. And so that leads us to the next section, which is about the local geometry of this least squares formulation. So here, quickly recap our models. So this, you have already seen it. So again, this is the generative model. The orange one is what I want to estimate. The blue ones are what I know. This is the least squares formulation again. And so for this, we first make some assumptions. And so these are kind of standard in some sense. So first of all, regarding the sensors, so these are the things whose position are known. I assume that they are sort of in a general position arrangement. So if you take the affine span of this, they basically span the whole Rn. Okay, so basically, in particular, you don't have three anchors all lying on the same line, and etc. And the second one is what I call a negligible noise. And so this is more motivated from the signal processing perspective. So with current hardware, they can actually give rather accurate range measurements. So I'm assuming the Wi, the magnitude of the noise, is much smaller than what I am trying to measure. Okay, and so this is the negligible noise. So this is a kind of still a qualitative assumption, but I guess one can formalize it, and once in the proofs, one can formalize this and make sure what kind of range of Wi is necessary in order to make the proof goes through. So this is the negligible noise assumption. So with this, we first have an estimation error bound, and so this is the answering the first question about the estimation error. So how far is the least squares estimator from the ground truth? Okay. Now, so it will be of this kind of order. So here I'm assuming the noise vector. So the W is basically all this Wi collected together. And I assume that it is less than square root m times sigma. So sigma is the variance or the noise power of each component. Then basically the estimation performance, the estimation error bound is of this form. So basically you see a sigma term and a sigma squared term. So naturally, if sigma goes to 0, then you reduce to basically a problem with noiseless measurements. Of course, then this is extremely easy because you have only one point to estimate. So there is not even rigidity questions to ask. So you just really just go ahead and solve it. And so, but as the noise goes larger, then we have this bound controlling the estimation error. And so naturally, when the noise power is small, then this will be small. So this is obvious from this. And picking this, because this is also, if one wants to impose a statistical model on the noise, let's say you want to assume that each entry is a Gaussian, then basically this is about the magnitude of the 2 norm of that Gaussian random vector, okay? And so if each entry is IID Gaussian with mean 0 as variance sigma square, then invoke your favorite concentration result, you basically get that the 2 norm of the W will be less than square root m times sigma with high probability. Okay, and so this is where this expression comes from. So partly motivated by the statistical model. But again, I should emphasize in this proposition, this is completely deterministic. I didn't assume that W has to be random. It just has to have bounded power, so a bounded norm. So this is our estimation error. And this result is not hard to prove. So I will quickly sketch, but it turns out to be rather crucial to our subsequent development. And so here is a couple steps of the proof. So here, first of all, recall our estimation problem. We want to find x so that x minus ai 2 norm square is roughly equals to ri square. So this is our problem. We want to find x to satisfy all these quadratic equalities, if you will. And then if you expand both sides, rearrange, then you get this form. So this is just expanding, nothing fancy. So I'm trying to find x so that it is close to this. So this is like a linear system, right? So if you collect all the i's on the left-hand side, so this is like ax equals b, right? So, and then so you can do a least squares. So ax equals b. So you try to find x so that ax and b are as close as possible. And so you just need to assemble what your a and b are. So the a will be like this. So because here it is I plus 1 and then minus the I, right? So this is just putting the a and the right-hand side into the b. And so for this least squares problem, you can find a solution. So this is just simple. And this here is where we use the general position assumption. And moreover, you can kind of reuse this argument again and again. Basically here, the original Ri is the measurement. Then you get the least square estimator like this. If you plug in Ri corresponding to the true range measurement, you can also repeat this argument and get the x star to be of this form. So you can basically subtract them, and then you get this expression. So if you subtract x star from xls, and then take the 2 norm, and this is basically the expression, okay? And then if you replace Ri with the range you get from the optimal solution, then you can repeat the same argument and you get a similar expression. And so this is the part of it. And then because I want to estimate the distance between x hat and x star, so right now, a very natural idea is triangle inequality, combining 4 and 5. But then I will, and a is given, so a is already fixed. So this is a number, and I want to estimate the difference between b and b star and b hat. And so using some algebra, basically they are of the order stated in the theorem. Okay, so that is basically it. And so using this, then we can actually show that the objective function of the localization problem is locally strongly convex around the maximum likelihood estimator. Now, so this is a little bit tedious. And so basically, we can go to the last line, which is the conclusion. So we can prove that the Hessian is PD in a neighborhood of x hat. X hat is, again, the maximum likelihood or the least square estimator. And so the neighborhood size is controlled by kappa, okay? And so what is kappa? So let us work backward. Kappa is this complicated expression. So there is a hopefully positive term in the first term, and then the rest are being subtracted from it. So being subtracted from it are terms involving the noise. So if the noise is small, then this will be good. This will make this more positive. And so we require the kappa to be positive. And so the first term involved 2 quantities, delta and lambda. And so what are these? So lambda, let me explain first. Lambda is this quantity, which is the minimum eigenvalue of this sum of rank 1 matrices. And what are the rank 1 terms? It is the vectors between x star and each of the sensors. Okay, so if you look at the sensor, and the source, then basically you draw the vectors from the sensor to the source, and then those are your vectors, and then you form this rank 1 sum. And so this, in some sense, incorporate the geometry of the problem. And so I will comment on this in a moment. And then there is still a delta. And the delta is for the first condition, meaning I need to assume that x star minus AI. So here is the ground truth, and AI must be sufficiently far. So in particular, the ground truth cannot coincide with one of the sensors. Okay, so this is, one can argue it is sort of reasonable in practice. If the thing you are trying to estimate is right on top of the sensors, then you should be able to know it. And so here delta is just a separation parameter that separates x star from AI. And so so let me first comment on this first condition. Why do we need it? Okay. Now, so first of all, as I already explained, this implies F is strongly convex over a region around x hat. The radius is kappa. Kappa is this radius. Now, why I need this? And that is because I'm talking about the Hessian of this. Okay. But I still need to be careful because my objective function, as I mentioned at the beginning of the talk, it is non-smooth, right? So at points where x equals to the AI, then the function is not differentiable. And so not let alone talking about its second order derivative. And so I need the first condition basically to make sure the x hat minus AI is bigger than delta. Okay, so I am actually away from the sensors. And so then at this point, it will be differentiable, in fact, infinitely differentiable. Then I can talk about its Hessian. Okay, and so this is the purpose of the first thing. Okay.
Okay, Anthony.
Yeah.
Another minute. Yeah.
Sorry.
So you have another minute or so?
Yeah. You want to ask a question now, or?
No, I think it's just that time is up. I was trying to get your attention.
Oh, I thought I have an hour. No.
Oh, is that my mistake? I'm sorry. Oh gosh. Okay, I'm sorry. Go ahead, please.
I do, right?
My mistake. Yes, you do.
Okay. Okay.
Oh gosh. Yeah. Thank you.
Okay. Thank you. Thank you, Henry. All right. So yeah. So that is where it is. Okay. And so here, as I was just explaining, so the condition here, I already explained the separation parameter delta. So that is just to make sure my result makes sense because the function in general is non-smooth. I have, it depends on the sigma square. And also in terms of the radius, it would depend on the number of sensors. And as I explained, this in some sense incorporate the geometry of the sensors. So for example, if you have x star and couple of the AIs are collinear, then this minimum eigenvalue will be 0. And then this will basically be void. Okay. And so this last condition kind of captures the geometry of the configuration. Now, however, this is still not very satisfactory. I think in some sense, if one can say more about how this captures the geometry, that would be more interesting. But this is what we have right now. So of course, by studying this term more closely, probably one can get more information about what kind of geometry will be favorable to solving this problem. And so once we have this, so then this is really a standard corollary. So you have a strongly convex region. So if you have an initialization in the strongly convex region, then if you run gradient descent, then basically you get linear convergence. This is a rather standard fact from convex analysis. This is one of the first results in Nestorov's book, for example. So this is just a simple corollary. So just to wrap up this part, so theorem 1 basically elucidates the geometry of the problem. So it says that even the function can be in general non-convex, but due to this generative model, if you make some assumptions, then you have local strong convexity around the maximum likelihood estimators or the least squares estimators. And so this one application, of course, is to explain the behavior of the gradient descent algorithm that is proposed first in Beck and co-authors paper. So they observed that the numerical experience is rather good, and so this perhaps can provide some insight on why that is true. Okay. Now, but just this result stand alone, there is still some challenge. For example, for the strong convexity region, whether you can explicitly compute an initialization that goes into that region is still a little bit challenging. So we know that we have this region, but how do we compute or initialize gradient descent into that region? That will probably need some work. But one natural idea is to try the XLS that I present earlier. So if you forgot what XLS is basically we derive from this manipulation. Okay, so as we saw, XLS can be rather close to X hat when sigma is small. This is following from 5 and 6. Okay, and so this may help to initialize gradient descent into the favorable region. But here, what I want to introduce and present to you next is another application, which is perhaps a little bit more interesting, is to provide theoretical guarantee for target tracking. And this is the problem where the source is not static, but instead is moving. Okay, so I guess this is a good time to pause a little bit to see if there is any question from the audience before we move on to a slightly different topic. All right, if not, well, of course, we can always save it for the end. Okay, so let us go to target tracking. And so this is the setup. Again, so here in this setup, I do not assume the anchors are moving. So they are static. The anchors are static. Okay, so they don't move. And I have a time horizon of interest. So that is capital T. And so I'm tracking this moving source in discrete time. Okay, so the time runs in 1, 2, 3 up to capital T. And so xt star, again, with the star notation, that is the ground truth, and that would be the source location at time t. So for example, here it is x1 star, and then at the next time step, it is here, and then it goes here, and then here. And so at each time step, you will get the range measurements. So this is the same model as before, except that you need to add another index of time in the expression. Okay, so here AI has no index of t because, as I said, it doesn't change with time. Okay, so every time step you have measurements, and again, WIT are the measurement errors at time t. So this is our setup. So the goal is to estimate the source location at each time step. Okay, so you want to do target tracking. Okay, so every time step you want to report or estimate what the source location is. So this is a very classic problem in control. So a classic approach would be, if you are from the control community, that would be Kalman filtering, but it usually assumes the target dynamics. So it requires you to basically have a model that models the trajectory of the source. Here I draw this dotted line, but I don't mean that I know its trajectory. I'm just saying it may be moving according to some flight plan, but I observe it in discrete steps. So in what follows, I don't assume that I have the trajectory information, or namely the target dynamics. And so here is a natural formulation for doing this. This is now in the time varying framework. So this is time varying optimization formulation. So everything is the same as before, except that you add the index t at wherever it is appropriate. So here, at time t, my loss function will depend on the measurement at time t. So this is RIT. And then I have my estimate x hat t here. Okay, and so that is my time varying optimization formulation. So this goes into the, I guess, the area of time varying optimization or online optimization. And so the main observations here are you cannot afford to solve this too accurately at every time step. Probably due to the fact that the successive measurements come in very short time interval. So you don't even have time to do a lot of computation, and then a new batch of data is already coming in. Okay, and of course, the sensors may also have limited computational power, and so you cannot solve it for every step very accurately. So, for example, you can't hope to run every step SDP on this, or you cannot hope to run you cannot hope to run gradient descent till convergence for this problem. Okay, and so this motivates us to use online methods, and so this is a very interesting, in my view, connection to online optimization and this localization problem. And so, what is the idea of online methods in this setup? Basically, you run an iterative method for a few steps, or in the extreme, you just run it for one step at every time step t. Okay, so basically, you have an initial point at time t, and then you just carry out gradient descent for one step, and then you need to move on. Okay, and so the question is, can this be formalized, and then whether you can say something about this kind of scheme. So here, let us focus on another classic scheme, and naturally connecting to what we have talked about in the first half of this talk. So let us use an online version of gradient descent. Okay, and so here is the sequence of events. So I always find it confusing when we talk about online optimization and time varying optimization, because I'm always confused about at what time step you are doing what. Okay, so for myself, I write down this. This is the sequence of events that is happening. So this is happening at the beginning of time t. So think of yourself at the beginning of time t. So these are the data you have. You have the location estimate from the previous time step. Okay, because you have been tracking, so you have the previous estimate. So you get, let's say that is called xt minus 1. And then you have the new batch of data coming in. So that is the new range measurements. So that is why the index here is t. So you have RIT. Okay, so you have the old estimate. So that intuitively you can think of is the point that could start your gradient descent iteration. But then you have this new range estimate, which you can use to define the new loss function at time t. Okay, so this is ft. And so basically online gradient descent says, then once you have these things, you perform one step of gradient descent. So starting from the estimate from the previous time step, you take one gradient step, and then you get your estimate for this time period. Okay, so xt then is the location estimate of the current time step. So here eta t, of course, is the step size, nothing fancy. So here, but notice this is ft. So I'm now minimizing with respect to the loss function at time t. Why can I do that? Because I already collected the newest batch of range measurements. Okay, and so this is my gradient descent. So if you are familiar with online learning, so this scheme is a little bit different from online learning. Online learning, basically, there is a very, very subtle difference. Here, instead of taking the gradient of ft, you are taking the gradient of ft minus 1. Okay, so you are doing prediction instead of doing optimization at time t. Okay. Now, if you are not familiar with that, then forget what I just said, because that may be causing more confusion than not. But if you are familiar with the online learning settings, so this is slightly different. So here, this is using ft. In online learning, they are using ft minus 1. Okay, because ft is not revealed to you until you commit to the decision at time t. Okay, so with that, we have this very simple scheme. To wrap up, to summarize, so basically at time t, I just run one step of the gradient descent, and then I declare the output as my estimate for the position of the source at time t. Now, so here then, raise a very interesting question. How should you evaluate the performance of such online algorithm? Okay, so in particular, you produce a sequence of estimate xt of the source location. How should you evaluate it? Again, if you are familiar with the online optimization literature, the first thing that comes to mind probably will be various notions of regret. Okay, and here is a rather general definition of regret. Basically, you are comparing the sequence you generate, which is xt, with a comparator sequence, which is x tilde t, and then you are comparing their difference in objective value. So xt is what you generate, x tilde t is the comparator sequence that you defined. Okay, and so so this is abstract. So if you take, for example, if you take x tilde t to be the optimal solution of the loss function at time t, then this will give you the notion of dynamic regret. Okay, and if you take x tilde t to be the optimal solution of the whole sum, then this will give you the usual notion of regret. Okay, and so this is the regret. Now, but we are not going to use this. Why? Although this is very standard in the literature, but if you think a little bit more about it, you are trying to track the source, but then this is just comparing the objective value of the loss function. And the loss function may not be a good measure of the tracking performance, because in some sense, the objective function is just a surrogate. It doesn't carry any meaning. The value doesn't carry any meaning, right? It just helps you to find the estimate. And so we are not going to use this, okay? What else is available in the literature? So they also have this tracking error. More specifically, they are analyzing this sequence. So they are comparing what you generate by the OGD and the optimal solutions, okay? Now, so this is comparing the distance between these two. And this seems to make more sense. However, if you think a little bit more about it, this is still not very satisfactory. Because if you use this, you are basically saying you want xt to be close to x hat, okay? So you want your OGD estimates to be close to the optimal solution of the loss function. But that is not what you want either, because the loss function is just a surrogate. And if you do this, you are just tracking the least squares estimate, but you are not tracking the true source location, okay? And so that is why this is also not satisfactory, again, despite the fact that it is widely used in the literature. So by now, you probably can guess what would be a more reasonable measure, and that would be comparing what you generate by the OGD with the ground truth, okay? And curiously, we tried to do some literature search. We can't really find similar definitions in the literature, in the online optimization literature, most probably because most of the problems they consider, there is no generative model, and so there is no ground truth, okay? But this measure, because we have a generative model, we have a ground truth, and so that is why we define this kind of error measure. And so to bound so with this, you can think of this as a new kind of regret. And so in the online optimization literature, a sublinear regret is usually a good thing, sublinear in the time steps capital T. And so how would that be possible? And so if you want to bound this, you basically need to control two things. So the first thing is standard in the time varying online optimization literature. And that is the so-called temporal variability of the target trajectory. And so that means xt star and xt plus 1 star cannot be very different. So your source cannot be too jumpy, okay? So if your source is taking quantum jumps, then it is very hard to track. But if it is something that is moving continuously nicely, then it is easier to track. And so the temporal variability is basically measuring xt star and xt plus 1 star, whether they vary by a lot. And the second thing is, since this is an estimation problem, obviously the noise level will again play a role in this, in controlling this error. And so that I already mentioned, you want a sublinear CTTE, sublinear meaning in the time horizon of interest. But if you try to do this, and if you try to get inspiration from the existing literature, you will pretty much immediately run into some difficulty, because most of the time varying or online optimization literature discuss convex objective functions. But here, our time varying loss function is non-convex. And so if you just try to apply it directly, then most existing analysis will not apply. Okay, but we have the local strong convexity that we established in the first half of the talk that could come to our rescue. Okay, so the idea is very simple. The rest is just implementing this idea, but the idea is very simple. So target tracking really is just a bunch of the static version of the localization problem stacked together. Okay, so you do it sequentially. At every time step, it is the static localization problem. So our earlier result says each FT will be locally strongly convex. Okay, so what you need to guarantee is the following. So at the beginning of time t, you are given the previous estimate xt minus 1, and then you have the current loss function. If you can ensure xt minus 1 is in the local strong convexity region of ft, then that means your initialization for ft is inside the local strong convexity region. You run one step of gradient descent, then you basically get closer to the optimal solution. Okay, and so intuitively, you can arrange this if the temporal variability is small. So this is what I just mentioned. So if the true locations are not too jumpy, and if the noise level is too small, then the optimal solutions of the two loss functions, ft minus 1 and ft, will be very close. Okay, and so if ft and ft minus 1 are very close, that means xt minus 1 will probably be also inside the local strong convexity region of the next objective function, namely ft. Okay, so that is the idea. So I hope that is clear. So basically, you try to keep yourself in the local strong convexity region of the whole sequence of loss functions. So what is the upshot of that? Then basically the whole problem just becomes a strongly convex time varying optimization problem. Okay, and then so you can utilize a lot of the standard techniques to help you do the analysis. And so here is the result. Okay, so that is basically just by putting together what I have just said, but formally writing everything out. So here are the assumptions. The first two are the same noise assumption as the static case, except that now I add the time index t. And then I also define this quantity Vt. It is the path length of the target trajectory. So this is rather intuitive. It is basically the length of it is basically the distance traversed by the source. Okay, so you are summing up all the segments. And then basically one can get the CTTE bound. So one can bound the tracking error. Basically, it has these terms. So these are the terms related to the noise. And this is related to the temporal variability of the trajectory. Okay, and so this is this kind of expression in terms of the terms that are involved in this bound are kind of matching what is in the literature. In particular, the literature always also have this VT, meaning the path variation. And so if this grows sublinearly, then you have a sublinear regret bound or a tracking bound. And here, if you have kind of sublinear growing or sublinear decaying noise, then you also have a sublinear tracking error bound. Okay, so this is the summary. So this is a little bit more tedious, but I think the main idea is really in this previous slide, meaning you are trying to keep all the OGD iterates in the local strong convexity region of each of the loss functions. Okay. So with that, that is about it. Those are the results. What I want to say at the end is the generative models are actually prevalent in estimation problems in signal processing. So although when we study optimization or tackling general, for example, theoretical computer science problems, we are always thinking about the worst case. But in this kind of practical applications, they are typically well accepted generative models. So you don't particularly need to justify them because it has been justified in the community. But then you can make use of this to see whether you can exploit them by various algorithms. In particular, with these generative models, it often leads to nice geometry of the optimization problems at hand, like local strong convexity or some other regularity properties. With those, you can design algorithms that exploit them, and then you can get sharper results from there. Okay, of course, one can think about many other problems. Here, by estimation problems, some of the more classic ones include phase retrieval, synchronization problems, etc. Those have been studied in the literature. Even, for example, matrix factorization, they have their also the generative models. For localization, of course, one can extend this to other setups, to other measurement models, or even extend it to the full sensor network localization problem, see whether one can say something about that. So there are still, of course, many things one can do and one can study. And so with that, thank you all for your attention, and that is all of my talk.
Well, thank you very much, Anthony. Yes. Well, do we have any questions? We have time for questions. And I just want to say that we do have a break till 10:30. So I guess we can stay around and ask questions for a while. Anything, is there something in the
Anthony.
Hi, how are you?
Hey, Anthony.
Hi, how are you, Steve?
I'm good. I'm good. Nice talk. Thanks. That was fun.
Oh, thank you. Thank you very much. Haven't seen you for a long time. Yeah.
Yeah.
Good to see you.
Yeah, exactly.
Very good seeing you. Yeah.
So
You are nice outside.
I'm in the backyard. Yeah, I'm on a swing. Whatever. Yeah, the weather's finally getting nicer here.
Yeah.
So actually, somebody has a real question, so I'll let you talk to him first in the chat.
Yes, I saw it. Yeah. So hi, Yongsheng. If it starts poorly, right. Yes and no. If you need to correct later, you will need something better than the gradient descent algorithm. So here we observe something that is very delicate. So here, of course, if you can also use second order methods, for example, online Newton to tackle this problem. The interesting thing is we observe that online Newton is very good at tracking the loss function, right? So it is very good at tracking the least squares estimator. And so it is not very good at tracking the true location, especially if the noise is large. But then it also says that it can track probably the thing more closely. So we are still not quite understand the trade-off between this. So the first order and the second order, when is it good for what kind of setting? So in this case, yeah, if it starts poorly, chances are there may not be a chance that you can recover very well. Yeah. unless you run more steps, I guess. You need more power, computational power. Here, I'm restricting myself that every step I'm only running one step of gradient descent, right? That is rather limited. So in order to correct course, you probably need to run it to a higher accuracy. Yeah, I hope that answers your question. But that is a very good question. Yeah.
Thanks. Sorry. So another question, I guess, was like, let's say if I, how does your method of like making steps updating one at a time compared to say something like I use not just like one time, but let's say maybe like a bunch of observations, or maybe the entire offline problem, and then maybe like apply, let's say, like a total variation penalty to make sure that the trajectory is like a bit smooth. Yeah.
Right. So, but then do you need to collect all of them, all the measurements, or at once?
Yeah, I'm cheating here. Yeah, that's true. I'm cheating here. Yeah, that's right. Sort of like asking, like, if you have all the comparing to the offline problem.
Sorry, it's a bit.
Yeah, I guess I'm sort of like trying to understand like maybe the difference with the offline problem is how far away these two solutions would be. I don't know if you have a sense of how far apart these solutions would be. So I'm thinking, like, I guess the offline problem, if you apply the maybe like a total variation, that's very expensive, but that may be sort of the most optimal thing given, let's say, the entire like history of the observations.
Yes. I think that is certainly possible. Yeah. So if you do the total variation or other kind of smoothing regularizer, then you can, in some sense, impose some structure on the whole trajectory. Of course, the key here is whether total variation is the right thing to impose on this, right? So because if you are thinking about smoothness, but here in this most general setup, I don't assume any structure on the trajectory of the source. So it is not clear. Yeah. So it really depends on your setting.
Thanks. Yeah, that's a good point. Thanks a lot.
Yeah, you're welcome.
So are you basically assuming that the thing is moving slower than the ability for your gradient descent to catch up to it?
Well, yes. So
are you getting, I mean, put it away. Are you getting, is the estimate getting closer and closer as time goes on?
Not necessary.
Okay.
Yeah. So it's not monotone, definitely, because every time I'm making one step, so it also depends on how the thing moves, right? And also,
sure.
Yeah. As you can see, the temporal variability will strongly affect how well you can do the estimation, because you can think of it this way. If the temporal variability is large, that means the successive loss functions are kind of the minimum will be far apart, okay? And then that means your previous estimate will be very far from the optimal solution of the next objective function. And so by just doing one step of gradient descent, you are still far.
Right.
Right. So then you are not able to track it very good. Well, yeah.
So, but in terms of, do you still get bounds in that setting, or is the bounds?
Yes.
Okay.
So here the bounds will be in terms of this variability quantity VT here. Yeah.
I see. So you're saying VT will be large, so you know you still have a bound, but it's not a good one.
Right. Yeah.
Okay.
Right. And your first question, yeah. So basically, I'm assuming I have time to do one gradient descent step before I collect the next batch of data. Of course, that is a very short time. So in practice, you may be able to run a couple steps of the gradient descent, and you can, of course, improve. But then the improvement will probably be, the same order. So yeah. So that is why this is a stylized model where people just go to the extreme and just carry out one step of the gradient descent. Yeah.
I see.
Yeah. But in practice, you certainly have time to run many more, I suppose. Yeah. Any other questions? things I can clarify.
So are you in? You're still in Hong Kong, right?
Yes, I am.
Do you see Pedro Sander ever? Do you know Pedro
No.
Sander?
No,
He
yeah,
does. He's in H. I forgot. Maybe he's in the other one. HKT whatever.
UST, yeah, University
Yeah,
of
he does
Technology.
computer graphics.
Yeah, yeah.
So
But although the city is small, but it is a mountain apart. So
okay.
yeah,
All right. Yeah.
I don't go over there too often. Yeah.
Okay. He's the
Yeah.
computer science department. So
Right. Do you know
Uh-huh.
any computer science graphics people in our university?
you know, I should look up to see who
You
they
probably all know
are.
someone too. Yeah, but yeah.
You know, also as time goes on, I know fewer and fewer of the younger people because I don't really work in that area much
Right.
anymore. So I have to look.
Yeah.
See, I should take a look. Hold on. So so where am I looking? Computer science, computer graphics, where?
Chinese
What's that?
University of Hong Kong. Yeah. CUHK. You can just type CUHK. Yeah.
CUHK.
HK.
Got it. Let's see. All right. Yeah.
See. Yes, Nathan. Yes. So what about weighted least squares?
Yeah, so you can hear me okay? Hi, good, how are you?
Yeah.
Good to see you too.
So yeah, what about weighted least squares?
So you mentioned, you mentioned weighted least squares at the beginning, and I
Yes.
was wondering if you looked into that any further, if you incorporated weighted least squares at any point into the theory or computations and how that would change things.
Computation we didn't try, but in terms of theoretical development, that wouldn't be too difficult, I would say. It's just pure tedious work.
Yeah.
So well, what you will have is basically a 1 over sigma I square associated with every term, right? 1 over sigma I square. And so if you want to do it in a lazy fashion, then you just, let's say, upper bound or lower bound all the sigma i's, then it will give you a same sigma, then it will return or reduce to the same setting that I did here.
Oh, I wasn't aware of this trick. So you say you upper bound the
all the variants by the max of all of them, right? So yeah, and then you can do the same thing, just like what I did here. Yeah. So that
would that change the solution if you use the same upper bound instead of using different weights for each?
Well, of course, in computation you wouldn't do that, but in terms of the analysis, that will, you know.
Oh, okay, I see.
Yeah.
I see. I got.
Then the bounds you get will be all suboptimal, right? So then it will be, you know, much looser. But,
I see.
But I mean, yeah, you get simplicity for that.
Yeah.
So I would say fundamentally it is not very different. Of course, in computation you shouldn't do that, right? So.
Yeah, because at times I've considered, we've considered a multiplicative noise model where if the distance is larger, then it would be more affected by noise. And so the weights then would be like 1 over the distance.
Yeah.
For example.
Right. So that would be very different from this one. Yeah. So then you have a fractional, you know, optimization problem, right?
Well, yeah, yeah, you're right. So it depends. It depends what you. So you could do like 1 over the measured distance.
Yeah.
So then it would just be a, you know.
Yeah, that would be a very different object.
It's but it would be an approximation for, you know, 1 over the true distance.
I see.
Yeah.